Hello everybody, welcome back to BEKU2333 Electrical Circuit 2. We're now in the chapter number 4, Frequency Response. Now we're going to learn a few things in this chapter. Upon completion, you should be able to find the transfer function of a circuit, get familiar with series and parallel resonance, identifying the category of filter, low pass, high pass, band stop, etc. and also perform some analysis related to this topic. What is the definition of a frequency response? It is the variation in its behavior of a circuit with change in signal frequency. It can be regarded as a complete description of the sinusoidal steady-state behavior of a circuit as a function of frequency. Now, what is the transfer function? It is also called the network function, a useful analytical tool for finding the frequency response of a circuit. Note that it is labeled as H omega, and we have X omega and Y omega. The transfer function is a frequency-dependent ratio of a phasor output Y omega, V or I, to a phasor input X omega source voltage or current. Now H omega, or the network or transfer function, is Y omega over X omega, and we have magnitude and phasor components. And there are four kinds of possible transfer functions. The first one is the voltage gain, voltage of the output over voltage of the input, current gain I output over I input, transfer impedance, which is voltage of the output over I input, and transfer admittance, which is I output over V input. From the equation of H omega, the transfer function, we also know that it is numerator n omega over denominator d omega. And we know that S is equal to J omega. Thus, roots of n omega are also noted as zeros, or roots that make the transfer function zero. And poles are the roots of d omega that make the transfer function infinity. To find the transfer function, we need to first replace R with the same R, L inductance with J omega L, and C capacitance with 1 over J omega C. Now let's look at an example. The question asks us to find the transfer function of V out over V in of the RC circuit in the figure below. There is a source Vi, and we have C and R in series, and the voltage output is labeled as the voltage across the resistance. And we know that that voltage is equal to IR, the current multiplied with the resistance, and the input voltage is equal to I, the same current, multiplied with R plus 1 over j omega c. 1 over j omega c is from 1 over sc that we learned from last chapter. Thus, h omega, or the transfer function, is equal to V out over V in, which is R over R plus 1 over j omega c. And this is equivalent to j omega rc over 1 plus j omega rc. Now the transfer function that we got was R over R plus 1 over j omega c. And let's try to divide this by R, and we'll get a simpler term. It becomes 1 over 1 plus 1 over j omega rc. Now we're going to change this a little bit. Let's try to move the j on top, and let's do this by multiplying with j over j. We'll get j over j squared, and j squared, as we all know, is minus 1. So that in turn makes minus j as the new term, and the whole term will change to 1 over 1 minus j over omega rc. Now we'll do something about this rc term. Let's change it to omega naught, and it becomes 1 over 1 minus j omega naught over omega. Now that was the transfer function, and we can get from this transfer function the magnitude plot and the phase plot. Let's try to look at magnitude first, and we'll get it as simply as 1 over square root of 1 squared plus omega naught over omega squared. And for the phase plot or phase term, we get it is equal equal to minus arctangent omega naught over omega, and this in turn becomes arctangent omega naught over omega. And proceed further on from the magnitude term, we can put some values in omega equals to omega naught. So that will be 1 over 1 squared plus 1 squared, or 1 over square root 2, and that is 0.07071. Sorry. And if it's omega equals to 0, then we'll have a magnitude of 0. If omega equals to infinity, then we get a magnitude of 1. And this will in turn makes a plot that looks something like this. It starts from 0 and ends at 1. At omega naught, the value is 0.7071. Now let's look at the phase plot. Theta is equal to arctangent of omega naught over omega. And if we put in some values, let's say omega equals to omega naught, our theta will become arctangent of 1. That makes it 45 degrees. If it's 0, then our theta will become 90 degrees. And if it's infinity, then our theta becomes 0 degrees. Right, this will make a phase plot something that looks like this. Starts from 90 and goes to 0 at infinity. In the middle, you will have something like 45 degrees at frequency of omega naught. Alright, let's go to another example. For the RC circuit below, obtain the transfer function V out over Vs and its frequency response, and let Vs equals to Vm cosine of omega t. Now the circuit is in series RNC, but this time the output voltage is the voltage across the capacitor. And to solve this, we'll use a voltage division. The transfer function will become H omega equals to V out over Vs, and that is 1 over j omega c because of the capacitance, and that is divided by R plus 1 over j omega c. And if we simplify that, we'll get 1 over 1 plus j omega rc using the previous method that was shown before. And to obtain the magnitude and phase plot, well, the magnitude plot is simply 1 over 1 squared plus omega over omega naught squared, and theta is equals to minus arctangent omega over omega naught. Notice the difference between the previous example. Omega is 1 over rc, and to plot h and omega, we obtain their values at some critical points, and let's sketch. Right? So we put in some values, we get the angle 0, minus 90, and minus 45, and h is 0, 1, 0, and 0.707. And we can plot it this way. H omega looks something like this. Starts with 1, decreases to 0. At omega naught, it is 0.707. And for the phase plot, it starts at 0 and ends at minus 90 degrees at omega naught, which is 1 over rc. The angle is minus 45 degrees. Going on to the third example. Now this time around, it is an RL circuit. And we'll find V out over Vs. V out is the voltage across the inductance, and Vs is the input. So to do this, the transfer function will obtain j omega L over R plus j omega L, and that is further simplified to become 1 over 1 plus R over j omega L. And by putting the j term on top, it becomes 1 over 1 minus j R over omega L. And the magnitude plot is 1 over 1 plus omega naught over omega squared. And the phase plot is simply arctangent omega naught over omega. And omega naught is equal to R over L. Looking at the magnitude and phase plot, it starts from 0 and ends at 1. And phase plot starts at 90 and ends at 0. If you go through step by step, we will see that these terms are divided by j omega L. And we get this term becomes 1 over 1 plus R over j omega L. And we will adjust j to become on top, the same steps that was shown previously. And you'll get 1 over 1 minus j R over omega L. And changing omega naught as R over L, this becomes 1 over 1 minus j omega naught over omega. And the magnitude plot becomes, a magnitude term is 1 over square root of 1 squared plus omega naught over omega squared. And the phase plot is minus arctangent minus omega naught over omega, that becomes simply arctangent omega naught over. And plotting this h omega, you'll get the term as shown. It's almost similar to the RC first example. We get a rising h from 0 to 1, and omega naught will have a value of h of 0.7071. And for the phase plot, theta is arctangent omega naught over omega, and putting in some values, we'll get uh, theta starts at 90 and then decreases to 0. At omega naught, theta is 45 degrees. So this is an exercise for you guys to do. You have a current source, an RL in series, and that is in parallel with a C or capacitance, and try to calculate the current gain and its poles and zeros. Now the answer is given here, and you can look at the solution yourself and try to understand step-by-step way of solving it. Alright, that'll be all for this lecture. See you again for the next lecture.